So I'm just going to speak just for a minute or two here to give people a very broad overview of the Open Academic Analytics Initiative, which Dr. Eitel Lauria's project and paper is a major component of. With only about a third of the students in the United States completing their bachelor's degrees in 4 years, I think probably I should have titled this slide "A Crisis Then a Challenge." It's a major national agenda in the United States, I'm sure for other people around the world. And so the Open Analytics, Academic Analytics Initiative is looking at the potential, as many of us in the room are, for learning analytics to really address this major challenge. We're doing this by leveraging two primary data sets. One's coming from our student information system, things like demographics data, aptitude data, as well as data coming from a learning management system, primarily event log data and gradebook data. And we're using this data to create or develop a predictive model with the ultimate goal of creating, and I think this is a little bit unique aspect of our project, an open source early alert system that will allow us to predict which students are at risk to not complete their courses and do that early on, the first 2 to 3 weeks. And then obviously, as we've all been talking about, deploy an intervention to hopefully make sure those students are successful. As I'm sure most of you in the room know, this is building on a lot of prior success. See John Campbell in the back room, obviously been a leader in this area, showing that course signals, for example, have produced, been able to increase student grades in courses and persistence from semester to semester. There's also some early evidence that interventions that use support groups have similar effects, and that's important because we're deploying interventions that include online student support communities and looking at how much that impacts on student completion rates. So we're building on this prior success by creating this kind of open ecosystem for learning analytics. That includes the Sakai Collaboration and Learning Environment, which is an open source LMS, if you're not familiar with it. The Pentaho Business Intelligence Suite, so these are data mining, integration, reporting tools that are open source. And I think a little bit unique too, we're going to be releasing our open source model under an our predictive model under an open source license using a standard markup language. So encouraging people to download this, play with it, enhance it, contribute back those enhancements. We're also researching critical, at least what we see as critical scaling factors. And so one of the big questions is around portability. How can you take a model that's built at one institution, let's say a research institution, and bring that to a different academic context, like a community college, and successfully deploy it there? And I think the first question is, can you even do that? But then what are the strategies to effectively move these predictive models, create knobs so you can adjust them as you move from one environment to another? And we're also looking at a range of intervention strategies, and we're in the process of analyzing that data and publish some research probably after the summer on that. So at the end of the project, we'll be releasing in a kind of a beta format, which we're calling the Sakai Academic Alert System. We'll have finished our pilots in about 36 courses at community colleges in the U.S., 36 historically black colleges and universities, which are, have a large percentage of socioeconomically disadvantaged students, and obviously putting out the research findings from that work. Last but certainly not least, all of this is being made possible through an EDUCAUSE Wave 1 Next Generation Learning Challenges grant funded from Bill and Melinda Gates and Hewlett Foundation primarily. And we'll be running this grant through January 2013. And so sometime shortly after that, all this stuff will in a sense come out. So with that, I'll turn it over to Eitel. We'll talk about the research we've done.
Okay, hello everybody. Let me switch the slide. So I'm Eitel Lauria. I'm the analytics lead in this project. I'm also Josh's partner in crime in this project, I guess. We're going to talk a little bit about the predictive modeling research overview. The focus, and actually it's the focus of the paper, the focus of the paper is the development and initial deployment of an open source predictive model. The idea was to develop a methodological framework for model development and be able to come up with some empirical analysis of predictive performance. And actually we got some preliminary results. Actually I have a So this is a mall development framework. What you're seeing here is what we have at this point, basically. I don't know if I'm getting there. Yeah. I don't know if it gets there. Well, Maris has data, as Josh was mentioning, basically biodata and course data coming up from our ERP system. Then Maris has implemented Sakai. Sakai is a course management system, an open source course management system, from where we're getting two data components. On one hand, grades and events generated by the course management system. The whole idea is, well, we go through a process of extraction, transformation, and loading, and I would say that we get into a kind of textbook and data mining methodology in the sense of partitioning the data, doing the training of the data, balancing the data. I'm going to explain this a little bit. Doing, creating a number of predictive models, and from there creating a library of predictive models from where we can actually score new results and obtain some results. Actually, I should mention something. Down here is the source data coming from our partners. What we have been doing initially is creating our own models using data coming from Maris, but we have been collecting data from our partners with which we are scoring some of the data. So in terms of challenges, there are a number of challenges that we've faced at this point, some of which we thought would be interesting to actually share with you because it's an evolving issue. Well, we know that data mining and predictive modeling is affected by input data and the quality of the data. Predictive models are as good as the data that you have. And so, well, good things about this, we have lots of data. I think Tim McKay was mentioning today, well, we do have data. The question is, what is the quality of the data that we actually have? And what are the factors that actually impact the quality of this data? Well, a number of things that we've found: variability in the course management tool usage. We find that faculty members use a variety of tools, but they don't use them all. So that means that we pretty much have huge holes in the data. Variability in the instructor's assessment criteria. That is, not every instructor grades in the same manner. There are hard graders, there are graders that are a little bit more lenient. So we need to, in a way, deal with this to, well, level the field in one way or the other. Variability in workload criteria. When we're considering course management events, you have faculty members that post stuff 7 or 5 days a week. You have faculty members that post stuff only once or twice a week, or once in a fortnight, for example. So variability in the multiple instance data, that is partial grades with variable contribution. Things that we're getting at is that faculty members grade in very different ways, actually assign names to the let's say, gradable events in different ways, and that actually affects the chances of automatically creating, let's say, predictive models that are able to capture this data from the structures. So another aspect which is not so good, the fact that we have imbalanced classes. In the case of Maris, we probably have around 6% of students at academic risk. Really, it's actually a little bit less. That's a number coming out of fall 2010. Depending on the semester, we're probably around 4 or 5. That's fantastic for the student body. It's not so good for the data miners, I guess, because we have to deal with some of those issues in terms of coming up with some of these models. In terms of the variability, well, there are some easy fixes that we can find. When it comes to variability in instructors' assessment criteria, variability in workload criteria, variability in periods used for prediction, in any of those cases, we've used ratios, and it's been effective in the sense of computing percent of usage over average percent of usage per course, or computing weighted score divided by the average effective weighted score when it comes to gradebook data. We've used different metrics. We've used averages. We've used medians, depending on how skewed is the data. And that has been, we've got good results. Where it's much more complicated is what I was mentioning before. The variability in Sakai's tool usage, it's an ongoing issue that we're trying to solve. Actually, we've had discussions with people from other universities, people from University of Michigan, actually, and this was one of the issues that was raised because we cannot do really data imputation in that case. That is, if a faculty member is not using a tool, we cannot invent the data. I mean, data imputation has been used forever in different disciplines, but sometimes it goes beyond the ethical issue of inventing data, is that you cannot do that, basically. So that's actually an issue that we're trying to deal with. On the other hand, the alternative to that is actually eliminating the data. But we know that when we eliminate the data, we're biasing the data because we are removing whole courses dealing with specific tools. So again, that's a problem that we're still trying to address in a reasonably scientific way. When it comes to the predictive models themselves, as I was mentioning, well, we need to balance the data, and we need to consider some metrics that, in a way, will measure this in a better way. Using accuracy metrics in highly imbalanced data is probably not a good idea, so we'd resorted to some other metrics, some of them coming from information retrieval, I would say, such as recall or precision, and those are the metrics that we were using in our paper, actually. In terms of the predictive models, in the case of this particular paper, we use three different algorithms. Actually, we use basically a logistic regression. We use boosted C 5.0 decision tree, and we use support vector machines, three, I would say, state-of-the-art algorithms to make some comparisons. We've developed a number of models. What you're seeing here is a conceptual layout of the model. Just to give you an idea of the kind of tools we were working with, we used two tools to try to be ecumenical in the sense of commercial tools and open source tools. So you're going to see, and I'm not going to go into the details, but perhaps it's useful to understand that, in a way, the flows that were reflected in my previous conceptual framework can actually be displayed visually through a data mining tool that goes through the whole process of doing the data pre-processing of the data set, doing the balancing of the data, doing the partitioning of the data, doing the training of the data, doing the testing of the data, and eventually scoring new data. In this case, we're talking about Pentaho Weka. Weka is actually a very popular tool in the data mining community. It's a Java-based open source tool. And we did this with this set of classifiers. We also did this using IBM SPSS Modeler to try to, in a way, compare tools coming out of the commercial field and the commercial domain, I mean, and the open source domain. And of course, we obtained more or less similar results, but it was interesting to, in a way, envision different tools, implementation of those tools using this conceptual framework that we were using. So, in terms of portability issues, as Josh was mentioning, first thing that we did was to try to see in what manner the data that we have compared with Campbell's original dissertation data. We actually found some similarities. The two institutions, actually Marist and Purdue, have some similar metrics, and that may perhaps be one of the reasons, but we were encouraged by that fact, and so we made some comparisons between some of the events generated by our course management system, in this case Sakai, against what was being provided by Blackboard. There are, in some cases, well, we basically were able to compare those events that were actually comparable. So, for example, number of sessions that a student would actually open in the unit of time, amount of content that was being viewed, discussions, amount of discussions that were read, discussions posted, assignments submitted, assessments submitted. In every case, although the original research was based on quantities, we actually did the conversion into ratios because of the reasons I explained before. This is our experimental setup. We took fall 2010 data with a collection of predictors. We reduced the collection of predictors because of this fact of huge amount of missing data within the course management event data. So we composed, I would say, data coming from the demographics, some of the, let's say, course data that measured final performance of the student. We considered a number of the course management systems for which we have reasonable amount of data, and we included a score metric that is basically, in a way, composing partial grades collected throughout the semester, or during a period of the semester, I would say. We defined the target. In this case, this is basically a classification for which we defined academic risk for any student that had less than a C, and everything, well, above a C was basically students that were in good standing. For this, again, we run using the tools that I was describing before, just for the purpose of coming up with a validation of them all. What we did is we repeated this 5 times so as to create 15 moles, and in a way try to at least come up with a mean and a standard deviation that would give us a better idea of whether we were just picking on a, let's say, singularity, or this was stable over the moles that we were analyzing. And these are some of the results that we actually obtained. It's interesting to perhaps, let me see if I can point on this. It's interesting to take a look at this data over here. Some of the results that we actually obtained is that logistic regression and support vector machines was doing much, much better than decision support systems, and that's an ongoing exploration. We couldn't actually figure out why that was happening. Probably didn't have all the time. Generally speaking, decision trees are usually very robust classifiers, but they were not performing very well, and that was kind of surprising. I put this little table in here just for you to, in a way, visualize some of the metrics that we were basically using. We're using recall. Recall is typically the true positives divided by true positives and false negatives. It's usually a very good metric when what you have is very unbalanced data. And for that, we were obtaining pretty good values. If you take a look at recall up here, we were around 82% and 87% in the case of logistic regression. The decision trees were actually not doing very well. Let me just point, I don't know where I am here. On the other hand, as a caveat, I would say we got a large number of false positives. Yes. And again, this is something that we need to explore further. It may have been due to the fact of having biased, in a way, our data set as to balance the data, considering that we had only 6% of the data with students at academic risk. But again, this is something that we still have to explore with more detail. So some results from logistic regression, the composite score extracted from gradebook data appeared to be one of the best predictors. And again, that's kind of in line with what one of the initial talks today, Tim McKay, was saying. It's kind of a tautology. Good grades, in a way, drive good grades in general, in a general manner. But the fact that we are able to collect partial grades are useful. Academic standing and cumulative GPA in second term, and it appears that CMS data is, in a way, kind of a second tier. Actually, I'm going to go to the conclusions. We don't have much time, I guess. Results are encouraging, although the number of false alarm raises some concern that we need to explore. There are differences among the classifiers, in particular in terms of the decision trees. Again, I'm coming from computer science, so this is an area that I was particularly interested in exploring beyond the learning process in particular. The data quality in terms of missing values remains an open issue that deserves further exploration. The partial grades derived score remains as the best predictor, and CMS-generated events appear to be a second-tier predictor, which, again, in terms of further work, I'm finished with this slide. In terms of, I'm being run out of the room, actually. In terms of future work, well, we're migrating the platform into an enterprise computing environment, but initial or interesting facts to consider is further analysis of partial grades derived score and further analysis on CMS events. Again, without entering into any kind of learning theory, could we actually consider CMS events as a proxy for student effort? On the other hand, perhaps the way in which we're hashing the data, it's not the right way, and it's something that we have to explore once again. Different types of aggregation, and I think I'm going to stop here.
Questions? And line up at the bottom.
So how much is the outcomes of that study transferable to another Sakai system? So if we run also a Sakai system and we want to use your open source project, I guess we have different data. The data will be different. Maybe we have more, maybe we have less. How much of that project can be applied to another Sakai implementation?
Actually, fully, because in reality, something I did not mention here, but Josh was mentioning, was the fact that we were able to, in a way, use the models that we created. And I think the virtue of what we have done is be able to create a full methodology and implement it in a given infrastructure. So actually, if we get data which is properly coded coming from, I would say, demographics and course data, that may be difference in coding between different institutions, and we get Sakai data, we can very easily use our models for prediction purposes. I would say a couple of things on that. We're going to get always much better results if what we get from the other institution is training data from where we can derive models that pertain to the particular institution. The issue of portability is an interesting issue to study, but it's very difficult to think that you can really port a model unless institutions are very similar. You take, I don't know, huge state university with a high level of desertion of students, for example, low level of retention, compared against an institution like Mary's that has probably 4 or 5% of students not completing the course, or students at risk, I would say. And you would expect that there are going to be some differences. But again, the fact that we do have I would say, methodology in place, implemented as an infrastructure, would allow us to very easily, given the data, deliver models. That's the reason why, as Josh was saying, we're going to deliver these models together with the infrastructure that we have developed to the public in a way.
Okay.
I'll just briefly add that we're going to release an API for Sakai to deliver the event greenbook data out to a number of different open source and commercial analytics tools. So it's going to be at the Sakai conference.
Okay, thanks.
Oh, this was very interesting. The data set that you used for creating your models, that was a data set collected over a single academic term?
For this particular paper, what we used was fall 2010 data, and then what we did was test it with, I think, spring 2010. I mean, we did that. At this point, we have, well, actually moved forward, so we have now 2 full semesters of data. There were some issues in terms of variations of the events that were being generated by Sakai, so we decided not to go back, because we're not going to be able to find all the events. We need to, in a way, place a baseline on what we were doing. So we took fall 2010, spring 2011, and now we're making predictions on fall 2011.
So the concern would be that the predictions are based on a model that has a whole term of data in it, yet the events might change throughout the term. For instance, people who browse really early on might actually be at very little risk, but you might just be counting total number of browsing, and you have a model for the whole term. So your predictions will actually be for the end of the term.
Well, no, that's the point. That's the reason why we were computing ratios, because we were computing ratios not only across courses, but also across the amount of time that was being consumed for a specific period in which we want to make a prediction. That makes a complicated assumption, which is that the distribution of, let's say, effort placed by a student is uniform, which we know that it's not. And that's the reason I was saying that perhaps our analysis of making course management systems events second tier in terms of predictors may very well have to do with the way in which we are aggregating the data. It's very difficult to mold this except by, in a way, some initial assumptions that you have to place on the model. The whole purpose of this was to create the infrastructure and then see if we can refine the model in terms of perhaps considering other probability distributions for the way in which students behave, for example.
Well, even if you just took, let's say, the first week of data, trained your model based on that, but used the outcomes from the end of term, and then did another one that had the first 2 weeks, and another model for the first 3 weeks, and so forth, you'd have multiple different models, but they would capture what's important at a given stage. So let's say you have no marks information in the first week, so that attribute, is something that would prune out, isn't interesting. But here your CMS data might be really important. By the time the midterms come, I mean, the midterm mark predicts the final mark. I've seen this many times. After that, your CMS information really isn't all that important.
Exactly.
And so then this way you could have tiers of models that are useful at different times, different models.
Yeah.
Right. So I think we're getting into the details, which are very important, obviously, but there also probably need to move down to the bar this evening.